Hello guys, welcome to Solving Solutions, your number one channel where you get solutions to all your solving problems. It's nice having you in class again today. How have you been? We are going to look at some important stuff in geometric geodesy, right? Good. So if you're coming to the channel for the first time, you can encourage us by subscribing to the channel. And if you are a returning viewer, thanks for always checking up on us. Now we are going to look at a question here. The question says we should calculate or compute the principal radii of curvature. We have two, that's the radius at the prime vertical and the radius at the curvature of the meridian, right? Good. So we should compute these radii at 5-degree latitude interval from 0 degrees to 90. So one thing you need to bear in mind is that it's going to be quite an exhaustive video. We are going to move from paper to computations like using some programs, right? Good. We are going to move from paper to using some programs. So this is not the end. This is actually the beginning of the beginning. So on this video anyway, you are going to enjoy all of those on this video. So you just have to get your calculator and then your writing materials. So first thing is that in geodesy, we know that there are three surfaces, right? The earth surface, like the earth anyway, there are three surfaces. And we have the topographic surface, that's the actually irregular, undulated, in fact, so complex to be modeled, right? So complex for us to have any mathematical computation rather. So we now have different models. We have the geoid and then we also have the ellipsoid. Now, some of those are in your literatures. You can actually check them out. However, what we are concerned with now is that we want to look at three. There are three ellipsoids that have been specified here. Okay, there are three spheroids that have been specified here. We have the Clark 1880 and their parameters. We have the Doppler satellite system and its parameters, and then we have the IAC 1967 and its parameter. Right? Good. So we want to use these ellipsoids or these spheroids as we have them here. We want to use them to now determine the principal radii of curvature of each of them at different intervals of 5 degrees from 0 to 90. So the first thing is that you can check out the literature in any of your geodetic maybe your geodesy textbook rather, and then you can see exhaustively what some of these radii mean, and but for the purpose of this video, let's see if we can just give an overview of what we have here. Now, at any point on the ellipsoid, there are two principal radii of curvature. We are actually reading from the Fundamentals of Geodesy by Professor Fubara, Professor Fajin Mirokun, and then Professor Ezeigo, right? Good. We are reading from their textbook. So, at any point on the ellipsoid, there are two principal radii of curvature. One of the curvature is in the plane of the meridian. That is a plane passing through the point and the north and south poles, or containing the rotation axis. This is designated as the meridian radius of curvature M, which is this, right? The meridian radius of curvature M. The other is in the plane of the prime vertical, which is perpendicular to the meridian plane at that point rather. It's called the prime vertical radius of curvature N, which is this, right? So from RAP 1991, we dealt with the derivations and also towards 2003, the meridian radius of curvature is this. So it was now spelled out. So we actually read it out from that textbook. So now let's look at the question we have. So before we move on, we actually wrote out some set of formulae we are going to use. So we have this small letter v equal to, it's actually equivalent to n. And what's our n? According to what we just read out, our n is what? The radius of curvature of the prime vertical, right? Good. So our n is equal to c over capital letter v equal to a over w. Now, maybe most of these parameters might be so vague to you, maybe you might not really understand them. So we went ahead to bring out more simple, or let's say simpler parameters of these same expressions that will make our computation easier for us, right? Good. So we also have p, because the two radii of curvature we have as p and v. So we also brought out p, which is equal to c over v cubed equal to a into 1 minus e squared over what w cubed equal to m. So this m and this n also have equivalents here, right? Good. So the the formula we adopted in this particular video are these two formulae you have here, right? So for the m, what's our m? The radius of curvature of the meridian, right? Good. So we have it as what? A into 1 minus e squared, all divided by what? 1 minus e squared sine squared theta raised to power 3/2, right? Good. That's a very important formula in geodesy. Then we also have our n to be what? A divided by 1 minus e squared sine squared theta raised to power 1/2. So all of these formulae are very simple to know. They are very easy to memorize, and then you can actually use them in your exam, right? Good. Then we also have another very important formula at the eccentricity, because if you look at these are our two radii of curvature. You can see that the parameters are the A and E. You know what A means, and then you also know what E means very soon. So you know that the A and E, and from each of the spheroids given to us, we already saw A, B, and F, but we didn't see E. Therefore, we need to compute for our E, right? Good. And then our E is simply what? The eccentricity, right? Good. So we have the eccentricity as the square root of what? A squared minus B squared all over what? A. And it's the same thing as what? The linear eccentricity over A. And your A, as we told you, or maybe as we said, we are going to tell you, is your semi-major axis. So A is your semi-major axis, your B is your semi-minor axis, and then your F is what? Your flattening, right? Good. So you can get exhaustive definitions or explanations of most of these things in any geodesy text, right? Good. So we have what? E equals to the square root of semi-major axis squared minus semi-minor axis squared all over what? Your semi-major axis, right? So now let's now apply this formula. So if you look at our M, you can see that in M we have A, we have E. These are the elements, or yeah, these are the parameters that can help us determine M. And we also have the latitude. We also have the latitude. So we need like 3 major parameters: the semi-major axis, the eccentricity, and what? The latitude. So when we have each of these, or when we have all of these, we can now determine what our M is. We can determine what our N is, right? So you need a calculator by you. We still have our calculator here with us, because we need to be confirming most of the answers we have on our screen. Maybe there's a typographic error or something, right? Good. Now let's look at Clark 1880. According to the question, we are starting from 0. We are going to start from the 0 on our program. We told you earlier that there is a program, or there is a formula that we designed, right? Good. So we are going to start from 0 to 90. You'll see that exhaustively on the program. But for this particular manual computation, or for this computation anyway, we started from 5 degrees latitude, right? So for the first spheroid, we have what? Clark 1880. And what are the parameters? For the semi-major axis, we have what? 6378249 meters. Then for the semi-minor axis, we have what? That's B. We have 6356515 meters, right? Then our flattening is 1/293.47. So remember what we told you to be the formula of eccentricity. We told you that it's A squared minus B squared all over what? A. So what you're going to do now is that, on our last video, very important, we told you some tricks on how to use your calculator. It was actually a build up to this particular video, because we know that when you're carrying out some computations on geodesy, you should not approximate, you should not reduce your values unnecessarily. So it's always better you store your answers on your calculator. So there's a video, the link to that video is on the description section, where you can see exhaustively how we have explained as we have been talking, because we know we've been promising that video. So we have explained exhaustively how you can store values on your calculator and how you can recall those values. So please check out that video, check the description section of this video. You will see a link to that video, and then you can watch it and you get the best out of it, right? Good. So we are going to save A, B, and E. We are going to save all of our parameters on our calculator. Let's just start with that. So let's save A. So we have 6378249. Did I make a mistake? No, 6378249. So shift store. We are saving it in what? Letter A, because that's A. Then our B is what? 6356515. Then we say what? Shift store B. You can see this on that video. We're actually emphasizing. Then we'll save that. Now let's come to our formula for eccentricity. The formula for eccentricity told us that we should do what? The square root of A squared minus B squared. So we can simply say, if we don't want to do all of them together, we can just break it down. So we can start by saying A squared. Please ensure you are pressing your calculator. This thing is very important. When you've saved A and you've saved B on your calculator, then you can now follow through by saying a squared minus what alpha b squared, right? Good. When you do that on your calculator, you see an exponential number. Don't be scared. We are not using the exponential number. We are finding the square root of that exponential number. So you just press square root of answer on your calculator, right? Good. Then you should be able to see something like 526,096.3417. Was that what you got? That was what we got now, confirming it here. Was that what you got? Good. Now, divided by A. Remember the formula? We have what? Divided by A, as it's been stated here. So we just simply say divided by what? Alpha A. Can you see how fast this thing is? It will not take you time to be typing in, or maybe typing in all of those values again. Once you've typed them in, that's all. You just have to be recalling them. So it's actually very important you see that previous video, because it will help you as you move on in your completion on other completions that you've been doing. So divided by A, what do we have? We now have our eccentricity. If you are actually going along with us, you should be seeing something like 0.08248287919, depending on how long your calculator can give what your values, right? So that's actually your eccentricity. So we are going to store that eccentricity on what? Letter E. So I've actually stored it on letter E. Shift store what? E, right? Or let's say shift recall E, right? Good. So we've stored that on letter E, which means we can just be recalling in this our formula here. We can just be recalling what? A, E, and the only thing we are going to impute now is what? Our latitude, which is what? Changing, right? Good. So we now have our eccentricity. So now let's come back to our M. What's our M? As we told you, the radius of the curvature of the what? The prime of the meridian, right? Good. So we are now going to impute the elements of what? Of this formula, or the parameters of this formula. So the first thing first is that let's get our numerator. So we are going to split it into numerator and denominator, and please follow the order of operations so you don't make a mistake, right? Good. So now let's start with our numerator. So the numerator, we have what? A minus 1 minus E squared. So you can actually press that on your calculator like this. Just say alpha A, then you say maybe multiplication or whatever. But if you don't want to put that, you can just open the bracket. So we actually said multiplication, then we open the bracket. The essence of opening the bracket is for the computer, or maybe for your calculator, to know that all of these are together, because we know this simple, or let's say this basic mathematics, that is it board math or so. So we want the calculator to know that these two are together, so they don't just start multiplying them without multiplying them together. It's actually very important, so you don't have the wrong answer, right? Good. So you open a bracket and you now say 1 minus. Remember, you already have your eccentricity, right? Stored on your calculator as what? Alpha E. So you call it as alpha E, and then you square it. Then you close your bracket. Was that what you did? Did you do that? I said A multiplied by, you open a bracket, you said what? 1 minus E. Remember, you've already stored E on your calculator, E squared. You now do what? Close the bracket, and you hit what? Equal to. So by the time you hit equal to, you should be having something like this, which is what? 6334855.059. We actually confirmed that on our calculator right now. So that's your numerator. So we are going to store that numerator as what? C. So we save it as what? Shift store what? C. So we have our A stored, we have our B stored, and we also have the numerator in this particular M stored as what? Our C, right? Good. So now let's come down to our denominator. Now this denominator is actually very tricky, but it's very simple. So you just need to follow it through. Now the denominator has a complex set of parameters here. We have something like E squared, sine squared theta. We have 1 minus and raised to power 3 over 2. You already know that 3 over 2 is 1 over 5, right? Good. So raised to power 1 over 5 or 3 over 2. So do not get overwhelmed. It's actually very, very simple. So let's see how we go about it. So the order of operation I would suggest for you is that you follow through like this. The first thing is that we are going to find the square of this particular trigonometric identity. So what you are going to do now is what? Just please say 5 sine what? Sine 5. Depending on the calculator you're using, there will be a bracket attached to it. Just close that bracket and then put a square outside. If you do not close the bracket and put the square outside, it will just do sine 25 for you, because you know 5 squared is 25. Whereas you don't need sine 5 squared. You don't need sine 5 squared. You need sine 5 all squared. These things are very tricky. Just like the way you did the bracket here, right? Just like the way you put the bracket here. These things are very tricky. So when you press sine, depending on the calculator you're using, there will be a bracket attached to that sign. If there is no bracket attached to it, you should introduce a bracket, then you type 5 and then you close the bracket. When you close the bracket, it is now telling the calculator that what you want is sine 5. Then any other thing you do outside it is that you are trying to operate on that sine 5. So on your calculator, if you're using the Casio series, the 911 FX 991 ES Plus series, when you type sine, there is a bracket attached to it. So you just put 5 in it and you close the bracket. When you close the bracket, you now say squared. When you type squared, you just hit equal to, you have a very small number, 0.000. So you have it as a standard a significant figure or something like that. So that's not the end. So we have done what? We have done this particular part of the formula, which is what? Sine square theta. So since we have done sine square theta, we now say multiplied by what? Alpha e squared. Remember that it's still part of the formula. The formula is what? 1 minus sine square. 1 minus e squared sine square theta. We are trying to split it in a way that we believe it will be very, very convenient for you, right? Good. So we have done the sine square theta part. We are now multiplying that our answer by what? Eccentricity squared, right? Good. So you now say times e squared. You've already stored your e as what? Your eccentricity. So you square it. Then you hit equal to there. You have an answer, right? Good. Then the next thing you are going to do now is that you now do the subtraction. You now say 1 minus that answer you have. So you say 1 minus answer. You say equal to. So by the time you do 1 minus answer and you say equal to, good. Then the next thing you are going to do now is that you now say that answer raised to power 1.5. Remember that 3 over 2, as we told you earlier, is equal to 1.5, right? Good. So when you already have this particular, when you subtracted it from 1, you just say what? Raised to power, according to your calculator, you just say raised to power what? 1.5. That's 3 over 2. For you not to have any issues of putting everything in the bracket, you just say what? Raised to power 1.5. Then you say equal to. When you say equal to, you should be seeing something like this on your calculator, which is what? 0.9999224,815, right? Good. That's the value you should be seeing on your calculator. So that will now serve as our denominator. Ensure you follow us through. Ensure you press these things on your calculator to confirm. These things are very, very easy. They are very, very simple, and you can get them once and for all, right? Good. So that's our denominator. So we are going to save that as what? D. So we have saved that as D from our end. So what? Remember, we saved this our numerator as C, and we have saved this our denominator as what? As D. So what's the simplest approach now? The simplest approach is for us to just do what? C over D, right? So we just say alpha C divided by what? Alpha D. Is that not? Please do that on your calculator. So when you do that, you should be able to see 6335346.165 displayed on your calculator. We are actually having that right now on our calculator here because we are pressing it along with you. So that's your M. And what's your M? The radius of the curvature of the meridian. So we've actually computed one of the radius as they have specified in the 2 radii for us to what? Compute. So that's our M. The next thing now is what? At 5-degree latitude anyway, for this particular spheroid or for this particular ellipsoid, right? Good. So we have actually what? Calculated this this n for this particular spheroid. Now let's go to M. Also n rather. Now you know the parameters are still the same. When I mean the parameters, your A is still your A, your E is still your E, right? So we are still going to use those stored values. You see the essence of storing those values on your calculator, so you don't need to type them again. Else you would have been typing them one after the other. So now let's go back. We already know that our A is already saved because according to the formula, the A is not multiplied anything or it's not attached to anything. So we can always recall our A. So now let's just work on our denominator. And this denominator is very simple. So remember how we did this sine square theta the other time, which is for 5 degrees, right? So it's the same thing you are going to do. You just say sine 5, you close the bracket, you say square, right? Good. You hit equal to. When you do that, you multiply it by what? Eccentricity squared. So alpha E squared, right? You have another answer, right? Good. You now say 1 minus that answer you already have. You hit equal to. You have an answer 0.9999, but that's not the end. Remember that it is raised to power half. And in mathematics, anything raised to power half is actually square root. This is actually basics in mathematics, right? Anything raised to power half is actually square root. So whatever answer displayed on your screen, you just say what? Square root of that answer, and you should be able to have something like this displayed on your screen right now. Are we together? So we have 0.9999741 598, 59598. So we're having 41601. So approximately we are on the same track, right? Good. Then the next thing is for us to now calculate our n. And how do we calculate our n? Our n is simply a divided by this last answer. So there is no need for us to store this one. All we are going to do is just recall our a. So we just say what alpha a divided by the answer we have, right? So by the time we do alpha a divided by the answer we are having 6378413.819. So just an approximate just 0.001 or so, right? Good. So that's how you go about getting your what? Getting your m and your n. Are we together? We hope this was actually exhaustive enough. And remember, according to the question, we are doing it at 5-meter interval from 0 to 90. So we thought it would be too exhaustive and cumbersome to be writing them out one after the other. So we had to automate it. We had to do what automate. So maybe if you are giving that as an assignment, it's best you present it like this in a tabular form. You have your changing latitudes, which are in 5-meter interval. So we have 5 degrees interval. So we have 0 degrees, we have 5, 10, 15, down to 90, right? Then the values you're computing for are the two radii, which is what m and n, and they are in what they are in meters. So by the time you present your answer like this, it actually gives a credit to what your score, right? So when you have something like this, it's better. So you can present it like this in a tabular form. Now, as we told you earlier, we automated the process. So we are going to see you on Microsoft Excel for the rest. For the rest is we have 3 spheroids. We only did for one, and for one we just did for 5-degree latitude. So you know that it's actually cumbersome. It's actually long. So the same process you've done we have explained to you, that's the same process you are going to use for the other spheroids. That's the same process you are going to use for all of the other latitudes. So please, if you missed any point, you can always rewind, listen to it. We are so exhaustive. We took our time to painstakingly explain everything in bits and bytes, right? Good. So we are going to see an Excel very soon where we'll show you the simple formula that we have maybe generated or developed for us to do solve this particular problem. So see you on Excel very soon. Thank you. Good. So welcome to Excel. Actually, Excel is a very, very interesting software, like so helpful. It has really been helping me in my study, like trying to automate stuff because I'm quite lazy at some point. But I used to spend some hours trying to get some of these formulas. So am I really lazy? I don't know, but anyway, I feel I'm lazy. Now let's look at this. So this is for the three different spheroids that we are giving to us. We have for Clark 1880, we have for the Doppler satellite, and then we also have for the IAC 1967. So if you need this, you can actually check a link in the description section where you can actually download it at a token, right? Good, at a token. So you can actually access it at a token. Link in the description section where you can access it. Good. So now let's see how this formula was built. You need to pay very good attention because what we are going to do here it's automatically generated, but we have actually designed the formula. So the parameters given to us are what the A, which is this. We have our B, which is this, which is the semi major, semi minor, and then we also have our flattening. Now remember that the flattening is actually operated like it was how would I put it? There was a formula designed for it because it's 1 over. It's not a full number, so we just type equal to. In Excel, whenever you want to start any operation, you need to come to an empty cell and you type equal to. That tells Excel that you want to carry out an operation, right? Good. So we did equal to 1 over, that's the reciprocal, right? So that's how we got this our flattening. And then our latitude, as we have been told earlier, starts from 0 to 90, but we just left it at 0 to any other value we are going. So these are the formulae we are going to use. Instead of formulae we are going to use, we have our eccentricity. We have also explained all of these on the previous slide. Now for the eccentricity, how to get the eccentricity. Now look at the simple formula we use. The simple formula we use, remember that according to the formula for eccentricity, eccentricity is actually what? The square root. That's why you saw a square root here, right? Eccentricity is actually the square root of what? A squared minus B squared divided by A. Now look at A squared. A squared is actually what? Cell B3, which is this, right? Minus B squared. B squared is actually what? Cell B4. This is B, and then this is 4, which is this. Minus what? B raised to power 4. Let's say, sorry, that's it. divided by what? B3, and our B3 is what? A. So this is how we generated this particular formula to get what? Our eccentricity. So if you look at it, there are so many parentheses in this formula. The reason why we add some of these parentheses is for us to put all of these things together, as we were explaining to you on the calculator, because by the time we remove some of these parentheses without putting them together in groups as they are, we are going to make a mistake. So if you need this particular program, you can actually check the description section of this video. You will see a link on where you can access it at a token. Good. So this is how we build the formula for the eccentricity, right? So we now got our eccentricity as this. And if you use your calculator, you will see that the answer is actually what? The answer is actually the same. That's for the eccentricity. Now this is where the crop of work is. This is where the major work is. This is where we actually spend some time. Now, when we got one, all we did was to drag down. Immediately we got one, all we did was to drag down. So now let's explain this formula. Now remember what our m is according to the question. Okay, it's already here. What our m is what? M is equal to a multiplied by what? That's our numerator. We have our numerator to be a into 1 minus e squared, right? Now let's look at this, our formula. We already know that b3. Now before we move on, you can be seeing, maybe you are seeing dollar signs. Now these dollar signs help us to lock cells. It's actually an important trick in Excel. When you have a particular cell and you don't want, when you drag down on Excel, it actually goes to subsequent cells. But when you are working on a formula, which we have done, when you build a formula and you want Excel to just be taking each of these cells without referring to the next one, is when you use the dollar sign. I don't know if this explanation suffices for it, but the idea is that if we had not actually put in this dollar sign for this particular cell, by the time we are dragging down, let's come up a bit. This is B3, right? So this is B3. So by the time we are dragging down, it will come down to B4, it will come down to B5, it will come down to B6, and definitely come down to B7. And you know that anything from B5 to B6 is actually not what we need. From B5 to B6 to B7 to the end is not what we need. Because what we need is for A to remain as A, for B to remain as B, and for F, if we are going to use F, to remain as F. So when you have any formula you're building that you want it to just specify or to remain on that cell even as you drag down, then you now introduce the dollar sign. And by introducing the dollar sign, you don't just introduce it once, you introduce the dollar sign on the letter and also on the alphabet. That means if you're actually referring to cell B20, you introduce it before B, and you also introduce it before 20, not after 2 and 0. No, not after 2 rather. You introduce it before 2 of the 20, and you also introduce it before B of the cell B20, right? So we are referring to cell B3 here. That's why we did what? We used the dollar sign before B, and we also used the dollar sign before 3, right? So that's an explanation of why you are seeing those dollar signs there. Because like now for this particular for the values of the angles, the angles are changing and we want them to change, so we do not apply the dollar sign. This is actually a perfect example of what we are trying to explain earlier. For these other ones, we want it to be fixed. For the cell B12, which is our eccentricity, we want it to be fixed as we are continuing with our calculation or with the formula. For the cell B3, we want it to be fixed. That's our A. But for the cell A16, which is our angle, we don't want it to be fixed. We want it to be alternating, because that's actually the question, at intervals of 5 degrees from 0 to 90, which means we need it from 0, we need it at 0, we need it at 5, 10, 15, up to 90. That's why we did not lock this particular cell. So that's another explanation. Maybe by the time you get the formula and then you're trying to understand it, that's another thing you need to pay attention to. Good. So having explained that, let's now move on. So as we said earlier, there are different parentheses here. The parentheses helps us to put things together. So the first thing is, now let's look at our numerator. Our numerator is actually A multiplied by 1 minus e squared. And our A is what? Cell B3. As you can see here, that's our A. Our A is what? Cell B3 multiplied by 1 minus. Now, pay attention. This 1 minus was actually put in a bracket so that we can have everything together. If we don't put them in a bracket, Excel will just multiply through and it will not know that we're actually saying everything in the bracket is together. So please pay attention to that as well. So we say what? A multiplied by 1 minus our eccentricity squared. And what's our eccentricity? Our eccentricity is actually this particular cell, which is what? B12. So you can see it, B12. And we want B12 to be fixed. We don't want it to be changing, right? So you saw it as fixed using the dollar sign. Now remember that there was no dollar sign after 1. The dollar sign was just before 12 and before B, as we are telling you in the other, let's say, as we are telling you earlier, right? Good. So it was before B and 12, not after 1, or maybe because we are trying to split it. No, just B and 12. So it has been indicated that for B12, that cell is locked, even as we are continuing with what the formula, right? So raised to power 2. So when you want to do squared, depending on the particular maybe PC you're using, you just use shift, that's shift 6. Shift 6 will be able to give you square, right? Good. So shift 6 will give you square. So you have what? A raised to power 2, that's actually square. Then we close that bracket. Now if you look at it, there are 2 brackets after that. This first bracket closes this 1 minus e square bracket, and then this second bracket, as you can see, closes the other first bracket we opened for what? Our what do you call it, our numerator. Are we together? These things are very simple. By the time you get it, or even as you're following through, you should be able to get it. Maybe by the time you get the program, you will get it. And if maybe you don't want to go through the stress of maybe knowing how to develop it, you can just be inserting your values and you will get your answers, because these things are fixed, right? Good. Then we now come down to our denominator. The denominator was where we actually had a chunk of work to do. Actually, it was interesting when I was able to figure it out, because I actually troubleshooted. Good. So we have what? Divided by, which is this division sign you can see here. I think I should be using this, which is this division sign you can see here. Then we open the set of brackets. Now the first bracket we opened was actually a bracket for the whole of the operation. If you look at it, immediately I come to that bracket, there is a bracket at this end that is also highlighted. That shows that those 2 brackets are the same. And that bracket is actually the bracket that combines everything in our denominator together, right? Good. So that's the first bracket. Now we now come to the second bracket. If you look at the second bracket, the corresponding value for the corresponding bracket for the second one is actually towards this end as well. Then we now come to our 1. Why do we start with 1? Because actually the formula started with 1, right? Good. So now this one is the one you can see here into 2 brackets. Now the first bracket actually covers what? The first bracket actually helps us to cover up to this square. Let's see how that goes. So we have 1 minus, then we have what? Our e squared. And we already told you what our e is. Our e is what? B12, and we have locked it because we want it to remain the same even as we proceed, right? So our e squared, and squared is raised to power 2. Now multiplied by, remember that we have it together. Remember we have it together in a bracket, right? Good. That's this particular e squared. Now multiplied by sine radian. Now you will be asking, why do we have radian attached to our sign? We have radian attached to our sign because if you don't have radian attached to your sign, you would not have the equivalent of that particular trigonometric identity you need. On Excel, when you want to find the trigonometric equivalent, maybe when you want to do trigonometry on Excel, you must convert it to radian. Are we together? So that's where you can have the actual equivalent as you do have it on your calculator. Because if you actually have done sine A16, which is what? Sine 0, the value you will get will not be the correct answer when you press it on your calculator. So this is another thing you need to pay attention to. So we also have what? Sine radian A16. The sine radian A16 actually, this radian actually covers for that particular way Excel was built, so that you don't what? Get a wrong answer for what? A sine of what? An angle. Are we together? When you've done that, you now have what? Sine radian A16, and your A16 is what? 0. Remember that your A16 does not have a dollar sign. It does not have a dollar sign because we are not fixing it. It is not fixed. It's actually a continuation at the intervals, right? Good. Then raised to power 2. Remember, let's now look at this particular bracket. If you look at this bracket, you will see that this bracket started from after the radian. This green bracket, it started from what? After the radian. It shows that this green bracket has actually covered for sine 0. Remember what we did on the calculator? We said sine 5, you close the bracket, then you square it. So that's the same thing we have actually done here on Excel. So we have done what? Sine 0, we have closed the bracket, and we now did what? We now squared it. That's where you now see raised to power 2. Are we together? After we squared it, then we are done with all of these values you can see. Where is that our formula for n? We are done with all of these values you can see. Then the next thing is now for us to consider what? Raised to power 3/2. And we have told you earlier that 3 over 2 is actually what 1 over 5, right? So we now come down to this our last bracket. On our last bracket in the formula, we now close out everything. Now let us look at the equivalent of this our last bracket in the formula. By the time we try to toggle over this our last bracket, you can see that it's actually what on the first bracket here after your division sign. It's actually on the first bracket after the division sign because according to the formula, we have everything we have from 1 minus e squared sine squared theta. We have all of that raised to power 3 over 2. So by the time you come to this your last bracket, you now see that it's actually equivalent or it's actually in line with this our first bracket. Then we say raised to power what 1 over 1.5 because 3 over 2 is actually what 1.5. So when you have done that, you've actually determined or you've actually imputed everything on what on your denominator. So you just hit enter and Excel will automatically give you the value of your m. And as we have told you, the m is what the radius of curvature of what the meridian. So after you've done that, the simple thing you're going to do is to do what is just to drag down or to fill. So by the time you drag down, or Excel will automatically do what? Excel will automatically autofill all of the other formula using the formula you've actually designed. And as it's going down, if we had not put this dollar sign for some of these cells, you would see that we'll be making or maybe we'll be having error, and we actually did because I troubleshooted a lot. We actually did. So you will see that you'll be having some errors, and for you to maybe fix those errors, you now need to fix all of those cells that you don't want to change with the dollar sign, and they will remain like that. Then you autofill and you will be getting your values, right? Good. So for the 5-degree latitude that we did manually, you can see that we have 635, we have 346.165. If you go back to the previous slide, you will see that that's what we have. Then for the n, we also have what 637, 849, 637, 8413.819. And you can see that that's actually what we also got. We had 818, but when we are actually pressing our calculator here, we had 819. So the error or maybe the discrepancy is just too minimal for us to be bothered about, right? Good. So that's how you go about it. The same thing you do for n. The most important thing about the formula is that you need to understand how to use the dollar sign and also how to get the equivalent of your trigonometric identity by using what sine radian. So as we said earlier, if you need, because you definitely do need it, you need it for practice, you need it for helping yourself when you're working on when you're working on geodesy, right? Good, or geodetic surveying, whatever the case is. When you're working on all of these things, you need it. So if you need or definitely as you want to get it, just check the description section. You see a link that will have you access this particular file as a token, right? So that was how we did for our n as well, and we did what we dragged down. So for you to check if all of these things are correct, maybe as a student, or maybe as an instructor, or maybe a lecturer, or whatever the case is, the only thing you can do is just to take each of these. So this is for the Doppler satellite, this is for the IAC. The only thing you can do is just to take each of these parameters as you've seen here, store them on your calculator as we explained to you, then insert the parameters into the formula, and then you do them manually. Just take some values randomly, as we have 0 to 90. Pick any random value and check if actually Excel made a mistake, or maybe as we built the formula if we made a mistake. And I bet you we actually done that and we did not find any error. So this is how you go about computing for your principal radii of curvature of specified spheroid. Any other spheroid you have, you just need to come here given. You define the spheroid, maybe whatever the name is, maybe WJ64. You give the word the semi-major axis, the semi-minor axis. You give the word the flattening, and then at whatever interval you want to go, this formula remains. Then you do what this E will change immediately. You start changing these values because this E is dependent on A and B. Immediately you start changing these values, your E will change, and then when your E change, every other thing will also change. And then if you also change these values, also affects what some of these things you have here. So this is how you go about it. These things are very simple. Any part you don't get, you can actually rewind, go back, and then you see it, and you can exhaustively get the whole picture. And then I believe you are going to enjoy yourself learning it this way because it was actually fun. So yeah, we have actually provided a solution to this particular solving problem. We hope you found it interesting. We hope it was not boring. We hope it was exhaustive enough. If you actually got to this point, thank you for following us through up to this point. And you can actually leave a like there to encourage us because it's not actually easy. You can check the description section on how you can support the channel and how you can also get this particular file at a token. So you can also share with your friends, your colleagues, your students, any other person you know might need it, and you know you've actually done something very, very great and very important for them. So we are going to see you on our next video. Until then, ensure you keep being good at what you're doing. Do the best of the observations you can, and we'll see you next time. Have a nice time. Bye.